I'd like to welcome everybody to the Bell Prize ceremony. I'm Paul Brummer. I'm vice chair of this committee that manages to work hard to find a candidate. I will explain momentarily what the prize is. So in this instance, it's awarded by the Center for Quantum Innovation and Quantum Control. Established in 2009. We've been doing this now for some time. It's awarded in alternate years, and the original idea, which we still have, is to give the award to work that was done in the last 6 years, not somebody who's worked over an extended period of time. In the case of the current awardee, he has both of them, so that's kind of interesting. So the award itself carries the name of John Stuart Bell, and it was officially approved by Mary Ross Bell, who was the wife of John Bell, passed away a few years ago, and manager basically of his estate. So this is really an official prize. The selection procedure, I should say something about it, is quite rigorous. There's an international selection committee, which in itself is approved by internal and external scientific advisors. The committee actually is asked at the beginning whether this external committee, internal committees then asked whether this selection of high-profile scientific advisors is appropriate to award a Bell Prize, and then after that they diligently go through a whole series of nominations, go through a voting procedure. It's quite a lengthy procedure. And then after that, it still comes back to us to see if there are any objections, either internally or externally, to the choice of candidate. So it's quite I wrote it down here as a meaningful and exhaustive task. Actually, it's an exhausting task, to be quite truthful. So this year, we're pleased to recognize Professor John Preskill, Richard P. Feynman, Professor of Theoretical Physics at Caltech. With the 8th Bell Prize, the citation reads as follows: the 8th Biennial John Stuart Bell Prize for Research in Fundamental Issues in Quantum Mechanics and Their Application is awarded to Professor John Preskill for developments at the interface of efficient learning and processing of quantum information, and following upon long-standing intellectual leadership in near-term quantum computing. So Professor Preskill will deliver a talk about this shortly, but before that, we're kind of in an interesting place. We assembled 3 former PhD students of Professor Preskill, which span decades, to either speak about the science or speak about the person. And the first one is our own Hoi Kwang Lo, professor of physics and electrical computer engineering, a former student of Professor Preskill, who will introduce us to the person. Hoi Kwang, if I can find you somewhere. Oh, here you are.
Can people hear me? Yes. Okay, so good. I've been asked by the organizers. Okay, can people hear me now? I've been asked by the organizers to say a few words about Professor John Preskill, who's my former PhD supervisor. I'm local here at the U of T, so I'm very happy to welcome him here, and I'm really honored to be honoring him in this occasion here. Hopefully nothing that would make John nervous. Right? So, okay, so I think this fact has been said by Paul already. So he's the Richard Feynman Professor of Theoretical Physics at Caltech, the director of IQIM at Caltech, got his PhD in 1980 from Harvard. Stephen Weibert is his PhD supervisor. Okay, my connection. Right? I was a student. I was very fortunate enough to got my PhD from John in 1994 at Caltech in theoretical particle physics. Right? So, at that time, yeah, there we go, okay, sorry. So first of all, who's John Preskill? Right? That's a very philosophical question. Well, in this quantum world, of course, there are many answers to this question, and depending on who you ask, what questions you ask, and what measurement you make. And let's think about time evolution operator here. For a long time, really, right, I've known John as a theoretical particle physicist, very well known in the community. He gives things like monopoles and all that, extremely well known. But somehow in the mid-90s, he made a tunneling to quantum computing, and he became very famous in quantum computing as well. So I think these days people mostly know John as a quantum computing theorist, right? But there's a life before that. So what was my impression of John, right? Of course, a long time ago, right? Again, not too many things I could remember, but there's one thing I remember very well, which is he was a very good listener, a very good educator. And there are many aspects of it. One thing that we could remember is everyone knows about this at that time, right? So he had open door policy. So his office door is always open at that time. And anyone can just pop in, basically, and ask him any questions in theoretical physics. And he has such a big range of interests. You can ask him questions in string theory or in just molecular monopoles or whatever subject you have in physics, right? He would be happy to entertain you and listen to you. And the good thing is you can even ask very stupid questions. And he would never say that this is stupid. He would just try to entertain you and try to think with you and see what the problems are. So I think that's very good because for our children, right, it's something that we need to be able to talk to our supervisor. So John has a very high standard in writing books. In fact, there are two books that he has been working on. Quantum field theory and quantum information and quantum computing for a long, long time. Right? And I think the lecture notes probably are online. I think definitely the quantum information lecture notes are online, and maybe a quantum theory lecture notes are online as well. But for that reason, I haven't seen them published yet. So that's something that well, we're looking forward to, right, for that case. One thing less serious. John also has a very high standard for haircut. I remember one time when calculus professors discussed very excitingly, right, where they should have haircuts and which barber was sort of cheaper. So that was a criteria that most physicists use. Right? But John would just say, I would only get haircut by one particular barber, which is quite something. Right? So you can see how stylish John is. Well, John is a very good teacher. You can see that he's very productive as well. He has 6 students. Some of them are here. We'll be giving talks, like Gottesman and Nicole. And we must not forget he has other students too. Just give you some examples. Sandy Chiragi works on string theory, cosmology. You can see a big range of research areas in this list. Right? I shall switch from non-appeal vortices to quantum. And you hear from Daniel, of course, well-known for stabilizer codes and quantum stuff. And even there's a musician, right? Patrick McGowan is actually a music composer, right? That's quite amazing. And John is a very good gambler, right? We all know that, right? He's a better gambler than Stephen Hawking. Although that's not saying too much, really. Well, he's a popular communicator. If you look at his CV, well, you can see that here. He's on X, right? He's very famous on X with 140,000 followers. Right? That's an amazing number for a scientist. So, I mean, he's really well known in not just in the scientific community, but also outside, like public, which is good for science, I think, in general. And he's a great lecturer, and you'll hear from him himself. Right? So I don't need to say something here. Just in case you have any questions, you should ask John. Right? Don't ask me. Okay. With that in mind, I think I would just conclude my introduction and let John speak for himself. Okay.
That's fine. No, please. Don't leave us. Don't leave us yet. I just wanted to enlighten everybody on exactly what the award was for. It was, I read from the website. We have a very nice website in the Bell Prize. says Professor John Preskill has shown that quantum machines can learn from exponentially fewer experiments than number required in conventional experiments, demonstrated the difference in performance of classical and quantum machine learning models in predicting the outcome of physical experiments. He has proven that classical machine learning algorithms can efficiently predict ground state properties of gapped Hamiltonians after learning from other Hamiltonians in the same quantum phase of matter. By combining ideas of computational learning theory with methods of quantum random measurements, Professor John Preskill has contributed significantly to providing a new quantum classical interface. In addition, he has provided continuing intellectual leadership to the scientific community in near-term quantum computers. That's what the award is for. And you might say, does he get something physical? And the answer is yes. If you step up here, this is so you won't forget us. A medal.
I need a mic, huh? I should use this one.
Unless you're going to be walking around.
Oh, all right, I'll just stay put then. Oh, wow, how can I follow all that? Well, I'm greatly excited and honored to be here, particularly considering the previous winners of the Bell Prize, who are all amazing scientists with remarkable accomplishments. As Hui Kwong said, I've had a lot of students and also a lot of postdocs who have gone through my group, and many of them are now leaders in quantum science, and of course I'm proud of what they've all accomplished. I'm especially glad to see here today Hui Kwong, Daniel, and Nicole. Hui Kwong was a PhD student before he and I really were focused on quantum information science. We worked on non-abelian anyons, but shortly after Hui Kwong left Caltech, both he and I independently made a pivot towards quantum information, and within a few years he had made milestone contributions to the theory of quantum cryptography, an area in which he's still a major leader. Daniel worked on quantum error correction when he was a PhD student. He wrote a brilliant thesis, which is still a standard reference on that topic. He invented the stabilizer formalism. Nicole was the hardest student to recruit, I think, I ever encountered. She had many good options. She told me she wanted to do British physics. So I said, well, why don't you do British physics here in Pasadena? Which she did. By British physics, she meant using resource theory to address questions about the interface of quantum physics and thermodynamics. And it's to the credit of Nicole and her cohort that is no longer just British physics. She and others are leading the advances in that area all around the world. Now, as we heard a moment ago, wisely, the Bell Prize is intended for work done in the previous 6 years, in this case since 2018, so I'm supposed to talk about the contributions that are recognized by the prize, and I will get to that, but I'm going to confound the organizers by digging a little bit deeper into the history of our subject. And that'll give me an opportunity, since I'll be doing this from a personal perspective, to talk about my favorite topic, myself. But before that, let's acknowledge Bell, who, after all, we honor by naming this prize after him. It's been 60 years, there will be this fall, since the Bell inequalities were presented to the world. Of course, quantum entanglement was something that had been discussed for decades at that point, including in 1935 by Einstein, Podolsky, and Rosen, and Schrödinger, and Bohr. But until Bell, entanglement was just something weird about quantum theory. Starting with Bell, we recognized it as a useful resource, enabling us to do things that we can't do without quantum entanglement. He didn't describe it exactly this way, but what Bell described was a cooperative game with two players, such that by taking advantage of entanglement shared between the players, they could win the game with a higher probability of success than if they only had correlated bits instead of correlated qubits. So they used entanglement to do something to win the game with a higher probability. And that entanglement enables us to do things that we couldn't otherwise do is still a key idea that's driving our field. I also want to give a shout out to Dirac. As far as I know, he was the first to explicitly point out the grave computational challenge of dealing with many particles interacting quantum mechanically. Just a few years after quantum mechanics was formulated, Dirac pointed out that we have a theory of everything that matters in everyday life. It's the theory of electrons interacting electromagnetically with each other and with atomic nuclei, described by the Schrödinger equation. But unfortunately, those equations are just too hard to solve for many particles. I think Dirac was thinking about more than just a few electrons. And for good reasons, I guess. It took over 50 years before Feynman made the suggestion that if we want to solve the problem of many particles highly entangled, interacting in a very quantum way, that we should use a quantum computer for that purpose. He recognized it was a new type of computational model. He challenged the computer scientists to work out some of the consequences of that model. I knew Feynman. We overlapped for 4.5 years between when I arrived to join the Caltech faculty and when he passed away. And we talked a lot about science. We never talked about quantum computing. I knew he was interested in that, but I was not at the time. We did talk about computation, which he had been interested in his whole life. And we were both interested in quantum chromodynamics and kind of excited by an idea which was just starting to get traction in the early 1980s, that we could explore the non-perturbative properties of quantum chromodynamics that describes subnuclear interactions using computers. And Feynman especially liked this because it was done by evaluating his path integral, albeit in imaginary time, by Euclidean Monte Carlo calculations. And I think Feynman's realization at that time that Euclidean Monte Carlo wasn't going to give us answers to all the questions we're interested in about QCD. That was part of what stimulated him to suggest the idea of a quantum computer. He also said at the time that we just don't have enough processing power now to really quantitatively contribute, using our conventional computers, to our understanding of the strong interactions. That would happen in the future. He guessed it would be a few decades, and that was exactly right. It wasn't until almost 30 years later that these Euclidean Monte Carlo calculations really started to inform the particle physics program, and now they're a vital part of it. So we should keep a timescale like that in mind when we contemplate how quantum computers can eventually be used to advance our understanding of quantum physics. It, may be a few decades before we can do that in a really significant way. Now, it's interesting to look at Feynman's paper today. It's still picking up citations at the rate of about 1,000 a year, and he, makes clear what the problem is he's trying to address, that we want to do a simulation of many quantum particles with a computational cost that scales reasonably with the size of the system. He argued we don't know how to do that with conventional computers. And actually, a lot of the paper, a lot of the technical content was about Bell inequalities. Because he was Feynman, he doesn't cite or ever mention Bell. But he's really trying to explain that a highly entangled quantum system is different from a probabilistic classical system, and that's because of entanglement as encapsulated by Bell inequalities. Now another, well, of course he famously ended his 1981 talk by pointing out that quantum computing is a wonderful problem because it doesn't look so easy. And now it's 43 years later, and it's still a wonderful problem that still doesn't look at all easy. But we're making progress for sure. Deutsch made the important step of formalizing the notion of a quantum computer, defining the idea of universal quantum gates, and that was taken further by Umesh Vazirani and his student Ethan Bernstein. And although Vazirani was a theoretical computer scientist, it was clear his motivation was coming from physics. He was trying to distill the essence of what makes quantum physics different from classical physics in the form of a computational model. And Vazirani led to Shor, with Dan Simon making an important contribution in between. And the discovery of Shor's algorithm in the spring of 1994 really had an explosive impact. It deeply impressed me and many others. I'm not sure why, because I wasn't so much of a computational guy and didn't know much about computer science, but I was immediately fascinated by the idea that with quantum machines we'll be able to solve problems that we just couldn't hope to solve with conventional computers. You had to know somebody to get a hold of the paper. Although the archive existed then, Shor didn't post the paper on the archive, but I got it from Arthur Eckert, who thought I'd be interested. And then that June, I went to a program about black holes at the Newton Institute in Cambridge, and I was there for a month, and every day I was talking to people about black holes, but secretly, at night, I was trying to understand Shor's paper, which was difficult for me because I knew so little about algorithms and complexity and so on, but eventually I felt I had an idea what it was about. Now, although there was great interest, there was immediate skepticism about whether quantum computing is really physically possible. And this came from very good scientists. One of them was Bill Unruh. And just a couple of months after Shor started circulating his paper to those in the know, Unruh submitted a paper saying quantum computing will fail because of decoherence. He tried to estimate the time scale for a many-qubit system to remain coherent, and he argued it was just too short to do a computation that would be classically hard to simulate. And another very good scientist who was a skeptic was Rolf Landauer. Landauer, the hero of the physics of computation. I'm sure you know Landauer's principle that erasure necessarily involves dissipation. He wasn't worried about decoherence so much as the fact that a state vector in a very high-dimensional Hilbert space lives in a continuous manifold, and if our control isn't perfect, it will drift away from its ideal value very fast, and then we won't be able to get the right answer to a computation. Conceptually, the discovery of quantum error-correcting codes changed this. It came from Shor again, and also Andy Steen independently in 1995. Now, we were at Caltech interested in how to stabilize a quantum computer, and at that time I really had a mental block. I had convinced myself that quantum error correction wasn't going to work, but we could do quantum error detection, and I was trying to develop the idea that if we could use the quantum Zeno effect to continuously check whether the state was in the code space in order to prevent an error. And of course, that was wrong. So it was very eye-opening to see the papers from Shor and Steen. And I mention it just to emphasize that things that seem very obvious to us now were not so obvious at the time, certainly not to me. Shor and Steen were just talking about quantum memory, how to store quantum information in a noisy environment. But there was a big step to go from there to fault-tolerant quantum computing, to perform reliable quantum computations when everything is noisy, the gates, the measurements, everything we do. That required the theory of quantum fault tolerance, and it was Shor again who figured it out. We were thinking about that at Caltech, and we didn't know how to get universal gates without leaving the code space where the information was protected. And Shor had a solution to that, which was essentially to make encoded ancilla states and then verify them and use them to teleport gates. It's still an idea we use in quantum fault tolerance today. Now, Kitaev was also very active in this period and a major contributor. He was coming at quantum error correction from a more physical point of view. And in particular, he had a deep understanding of topological phases of matter and topological order. He made his first visit to the US in spring of 1997. He came to Caltech for a while. And the day I heard his talk, at which I took these notes, was a very memorable day for me. Because remember, I was working on non-abelian anyons with Hui Kwong, and I worked on quantum error correction with Daniel Gottesman. And I don't think it ever occurred to me that these two things were related. It took Kitaev to point that out. But I was well prepared to appreciate the idea as soon as he said it. And after sufficient repetition, I finally learned how to spell repetition correctly. Actually, Kitaev made a string of remarkable contributions in that time frame. And well, there's one time in particular where I momentarily, even though I know Kitaev, like Shor, is many times smarter than I am, I felt smart in comparison once. In the late 90s, I said to him, I think the toric code, the surface code, is going to be good for computation. And he said, no. The toric code is for storage. Non-abelian anyons will be for computation. I said, well, I think the toric code is going to be good for computation, but I can't figure out how to do universal gates on the encoded information. So he said he'd think about that. And well, I don't remember for sure how long it took, but it seemed like the next day he came back with the solution, which was magic state distillation to perform non-Clifford gates. It took another 5 years for the classic paper by Kitaev and Baravi to appear, but that's still a key idea for doing protected quantum computation today. And then there were many people contributing in the years following innovative ideas to quantum error correction. I mentioned Steen, Daniel, of course, Saharnov and Benor, Nilin Laflamme, and then a younger generation came up with many innovations. And now the field is really taking off, and the developments are just too fast for me to keep up. It's an exciting time. So we first started to talk about doing computation with topological codes in 1997. Well, it was a less crowded field then. It took 4 years before we finally wrote a paper about how to do things with surface codes and decode them efficiently and so on. There wasn't much competition. There were other people working on quantum error correction, but we could kind of take our time. And I want to give some credit to Jeff Kimball, who was my colleague at Caltech, and he impressed upon me that if he put atoms in a cavity to create nonlinearity, he could in principle make any quantum state of light that one might desire. So he challenged me and other theorists to come up with some really neat state of the electromagnetic field for him to try to prepare. And Daniel came to visit in the spring of 2000, and we came up with the idea of encoding a discrete quantum system in a continuous variable system using grid states. And at the time, this isn't fair, it's not universally true, but some experimentalists scoffed that this was just completely ridiculously hard to do. One who did not actually was Akira Furusawa, who Daniel and I knew from when he had been a Caltech postdoc. He took the idea seriously from the start. But generally speaking, it took about 20 years for people to start really pursuing GKP codes because we had to wait for the technology to mature to the point where one could really imagine making and using such states. Now, even after the theory of fault tolerance was in principle established, the problem was solved to the satisfaction of a theorist, we could make quantum computing scalable. Skepticism still existed. again, coming from very good physicists. One was Serge Haroche, who knows more than anybody in the world about decoherence. He studied it for years and won a Nobel Prize for that. In 1996, he conceded that quantum error correction in principle solved the problem of controlling a quantum system, but he said it would just be exceedingly difficult as soon as one has to deal with more than a few gates. In this sense, the large-scale quantum machine may be a computer scientist's dream, but it's an experimenter's nightmare. And I guess that's still true. It still looks really hard to make a large-scale, fault-tolerant quantum computer, and it's going to take a while to get there, but no question we're making progress, and I think there's much less skepticism now about whether we'll ever be able to do it. So by 1996, a lot had happened in 2 years, and one can sort of see what some of the big issues were going to be going forward. I think David DiVincenzo was responsible for this, and it wasn't an obvious thing to do in 1996 since I didn't have much of a profile in the quantum information community, but he asked me to give an overview talk at the conclusion of a conference, which was at ITP in 1996. There was no K then, it was just the ITP in Santa Barbara. And by the way, the culture of quantum information in those days, and as is the case now, was very welcoming. I was kind of an interloper coming into the field. I was a particle physicist. I thought people might resent that. Nobody did. In fact, they were quite delighted that somebody coming from particle physics was actually interested in quantum information. So I felt like I got integrated into that community very easily. But we could see we needed to come up with new ideas for speedups, polynomial speedups following on Grover, exponential speedups following on Shor. We needed to flesh out the idea of using quantum computers for quantum simulation tasks that would really advance science. We had to advance the theory of quantum error correction, make it more efficient, understand its broader implications for physics. We had to figure out what else we can do with quantum error correction and quantum information processing. What would be its implications for metrology? And how are we going to deal with all of the data that came from measurements in multi-qubit systems? How would we organize and make use of it? And these are still good questions today, though we've learned a lot since then. So my unpublished book came up. So I was really uncomfortable in 1996, 97, that I didn't know enough. I didn't really know quantum information theory. I didn't know information theory at all. I knew little about the theory of computation and quantum complexity and so on. So the best solution is to teach a course, which I did for the first time starting in the fall of 97, and I put the notes online. I was somehow oblivious to the fact that a postdoc at Caltech at the time, Michael Nielsen, was writing a book which would become the standard reference for our field. So for a while, this was the go-to source and that a lot of people made use of in the late 90s. And the point is I learned a lot from that experience of teaching it. I have to give credit to Jeff Kimball again. He prodded me in the late 90s to propose an institute for the theory of quantum information at Caltech. Without his urging that this would be impactful, I wouldn't have done it. And the National Science Foundation agreed to fund it and then to keep it going. It expanded 10 years later to become the IQIM, which is a balance between theory and experiment. Now the quantum institutes are everywhere. In the late 90s, it was really a novelty to have an institute devoted to this subject. And insofar as the existence and ongoing activities of these institutes has contributed to the advance of the field, that's something I'm proud of. Now, I used to say to people in the 1990s, look, quantum information isn't just about building a better computer. It's much broader than that. It's going to change the way we think about physics in many ways. And this was met with a lot of skepticism from physicists. Computer scientists liked it, even though they didn't quite know what I meant. They thought it sounded good. But physicists didn't really believe it. So I was challenged by Ike Chuang to write a manifesto about that. Actually, the way it happened was Ike who was then at IBM Almaden on the West Coast, was a co-founder of an organization called SQUINT, the Southwest Quantum Information Network, which still exists and puts on awesome annual meetings. I think this was the first meeting, and he said I should talk about what quantum information means for physics. And so, you know, I came up with, well, I thought it would be, I didn't really know how, that it would be important for quantum gravity, it would be important for quantum condensed matter, it would be important for quantum metrology. I remember talking to Frank Wilczek in the late 90s, and I said to him, you know, Frank, quantum phase transitions are really about quantum entanglement. And he said, oh, that sounds profound. And I said, but Frank, I'm afraid it might be trivial. And he paused for a minute, and he said, it's profoundly trivial. and what we both meant was, when you talk about phase transitions at zero temperature, you mean that there are qualitative changes in the structure of the correlations in the system, and the correlations at zero temperature are really about entanglement. So if there's a quantum phase transition, that means there's some sort of realignment of the entanglement structure of the system. And so somehow I thought that was a good idea. And actually, we already knew in 1994, thanks to Frank and others, that in conformal field theories, there are universal properties of entanglement. But we didn't know of such a property in the case of gap systems or topological phases of matter. And I noticed that in the toric code, if you cut a hole in the code block and ask how entangled is that hole with its complement, that doesn't depend on the shape of the hole. It's just, it's one E-bit short of maximal entanglement. And you know, I said to Alexei, well, this must be a signal of something more general. So he said he'd think about that. And then he went to Russia for his summer vacation. And when he came back, he essentially solved the problem, observing that there's a notion of topological entanglement entropy, which is a universal quantity and can be used to distinguish different gap phases of matter. So that at least convinced us that there was something to the idea that it was going to be a rich subject, that entanglement theory would be helpful for understanding phases of matter. Another time I was lucky was I was participating in an event at Perimeter Institute in 2007, and I happened to share an office with Patrick Hayden. And I knew Patrick well because he had been a postdoc at Caltech in the early days of IQI. And he had the idea at that time that then relatively new ideas in quantum information theory, what we call the decoupling principle, could be relevant for quantum gravity. And we figured out that if you had a black hole, for example, that was very entangled with its surroundings, like an old black hole that had been evaporating for a long time, and then you toss some quantum information in, that information would come back very quickly in the Hawking radiation. And that surprised us, and it surprised everyone we told about it. And so we wrote this paper with the objective of persuading people in both the quantum information side and the quantum gravity side that they actually had a lot to talk about. And so, you know, it's been gratifying to see how that interface has developed. If you're interested in the theory of quantum gravity now, you really need to know quantum information. You need to know about quantum error correction and quantum complexity and quantum entanglement. So I became somewhat notorious for proposing the term quantum supremacy, for describing that quantum systems would be far beyond the capacity of conventional computers to simulate. And the way that first came about was in the spring of 2011, Jag Shah, a friend of mine who was a program manager at DARPA, asked me to speak at an event that he organized. He had a program of really good physicists that he was funding. He wasn't funding me, but he wanted me to give this talk and sort of give some kind of an overview of quantum information for that very distinguished physics audience. So I decided to emphasize that, you know, we're getting close to the point where quantum computers will be able to do something, even if it's not something that's practically valuable, that we can't simulate with conventional computers. And that'll be kind of a milestone in information processing on Earth. This wasn't a very novel idea, and in the talk, you know, I was leaning on recent work by Aronson and Arkhipov and Bremner and Joza and Shepard. But because it involved complexity theory, I wasn't very confident. So I sent my slides to Scott Aronson and asked him to check if they looked reasonable. And I sent them in the evening, and he wrote back the next morning, and he said, "Oh, I'm so sorry it took me so long to respond. I'm in Israel. I'm about to get married, and I sprained my ankle yesterday, so I haven't been able to check my email until now." He answered in 12 hours. Anyway, he said the slides were okay. And then I had a chance to reprise that presentation later that year at a Solvay conference. If you're a fan of the history of physics, the Solvay conference has a kind of a special cachet. It started in 1911 when international scientific conferences were not commonplace. And so this was 2011. It was the 100th anniversary. The theme was the theory of the quantum world. It included everything. There was astrophysics and cosmology and string theory and particle physics, condensed matter, and so on. But I thought it was a sign that quantum information science was very well represented in overview talks by me and Steve Gervin and Ignacio Sirac. And people were really, it was the first time that broad a physics audience, in my experience, was really intensely interested in what was going on in quantum information science, and that's even more so true now. A few years later, a guy named Matt Johnson was organizing a conference called Quantum to Business, and he invited me to come, and I didn't really want to, but he called me, and he's a very persuasive guy, if you know Matt Johnson. He's hard to say no to. So I agreed to give this talk, and I decided that I should be making 2 points. One is these companies, which would be represented, really have to keep their eye on the goal of fault-tolerant quantum computing, because that's where the economic value of quantum computing was going to really kick in. But in the meantime, we were kind of at the precipice of having quantum machines that could do things that classical machines can't do, and whether they'll be useful things, we don't know, but we should try. And I realized we needed a word for that. So I made up a word, noisy intermediate scale quantum, NIST. And before giving the talk, I asked a few people, what do you think of this word NIST? And everybody hated it. But the community was hungry for a word, so NIST caught on. And I guess I'm going to mention the Solvay conference one more time, because the most recent one in physics, with a few exceptions, like this one was delayed for 2 years because of the pandemic, there's a Solvay conference in physics every 3 years, and they rotate. There's astrophysics, there's condensed matter, there's particle physics and quantum gravity. But this was the first time that the whole conference had a theme of quantum information. But quantum information aimed at advancing the physical sciences. So these other fields, like quantum gravity and condensed matter, were represented, all focused on how our quantum technology and our ideas about quantum information were going to advance those different disciplines. So I felt like that was a real milestone for our field as well. It's now clearly part of the mainstream of the physical sciences. Okay, so you wondered if I was ever getting around to why I won the Bell Prize. How much time do I have? Hopefully I don't see anybody. Are you already standing up? 5 minutes? Are you kidding me? Okay. All right, that should be enough. Oh, okay. Okay, so here's why I won the Bell Prize, because of these two guys. Robert Huang was a PhD student who arrived at Caltech in the fall of 2018. At that time, Richard Kuhn was a postdoc. And Robert, when he arrived, already had significant research experience in machine learning, a subject about which I knew nothing. And as of now, what little I know, I learned from Robert, who knows much more. Richard actually volunteered to teach a course on quantum information and tensor networks and probabilistic methods and tomography and so on in the spring of 2019. And that ignited a collaboration between Robert and Richard, which I joined. And my role, if I had one, was to steer the project more towards protocols that we might be able to carry out with relatively near-term technology. So we wrote this paper in 2020, and several follow-up papers which were mentioned in the description of what's being recognized by the prize. So the attitude we were coming from is, look, it's a quantum world, but we are classical beings. Sometimes our classical nature can impede our ability to interact with, learn from, and understand the underlying quantum reality. So we want to know, how can classical and quantum machines enhance our ability to learn about the quantum world? So when I speak about learning about quantum systems using classical machines, what I have in mind in particular is the possibility of converting a complex many-qubit quantum state to a succinct classical description of the state. We can do that by discarding a vast amount of information, but the point is that we can retain a lot of physically relevant information which we can use to predict properties of the system. Then we can apply classical processing and classical machine learning tools to generalize and try to predict properties of systems we haven't yet encountered in the lab. And we can learn how to recognize when new quantum phases of matter have been created in the lab. As far as learning about the quantum world using quantum machines, we envision that a future sensing platform will be able to capture quantum data in the field, transduce it to a quantum memory, and then process it with a quantum computer. And we argued that for some tasks, by doing so, by using quantum processing, we'd be able to learn properties of the signal with an exponential advantage. The number of experiments we would need, the amount of data we would need to collect, would be exponentially smaller if we use quantum processing instead of conventional sensing and classically processing the results. Now, the idea that we can describe a quantum system with classical data, everybody knows, but for a many-qubit system, it's just not practical to do that, because we would have to write down more bits than, well, we would have to write down an exponential in the number of qubit number of bits. To acquire that description, we would have to do a number of experiments, which is exponential in the number of qubits. To use that description to extract predictions, we'd have to do an amount of classical processing that's exponential in the number of qubits. But we can take the point of view that we don't need a complete description. We'd be satisfied with a much more succinct description that we can use to predict properties. And here we were drawing a lot of inspiration from work by Scott Aronson, which preceded ours, in which he spoke of shadow tomography. He was making the distinction between complete tomography and the ability to predict the expectation values of many observables. So Scott's work was very inspiring, but it wasn't at all practical, because his protocol required measuring observables that act collectively on many copies of a state and that require an exponential amount of quantum processing. And we wanted something that was more practical. So the goal, which we called classical shadows of quantum state, was to come up with a way, by doing a small number of experiments, which are all feasible with current or near-term technology, to acquire a succinct classical description of an unknown quantum state from which we can predict many properties, where we have a rigorous guarantee that our predictions are accurate with high probability. And so examples of things we can predict with classical shadows are the fidelity of an unknown quantum state with a known target state, expectation values of local observables, local Hamiltonians, few body correlation functions, and so on. So here's an example of something we could prove. So let's say we would like to be, there's an unknown quantum state, and we have the ability to access many identically prepared copies of the state. They might be prepared by a quantum computer, or by some protocol in the lab, or by some other procedure. And our goal will be to predict the expectation values of many observables, which are guaranteed to have a weight, a number of qubits on which they act non-trivially, at most W. And here's the procedure that we do in the lab. It's pretty simple. For each one of the copies, for each one of the qubits, we randomly choose to measure that qubit in one of three bases, the poly X, Y, or Z basis. So we collect a bit string from every copy of the state. The collection of bit strings is our classical shadow of the state. And we could show that from these snapshots, we can efficiently, with efficient classical processing, compute an approximation with a small error to the expectation values of altogether m observables, which have weight no higher than w, and the number of copies that would suffice for that purpose grows only logarithmically with the number of observables that we want to predict. If we want to predict higher weight observables by this method, then there's an exponential cost in the weight, but if we bound the weight, then we can predict a number of properties which is exponential in the number of copies. And we can apply the procedure also to estimating nonlinear properties, functions of the density operator, like Rényi entropies, which you can think of as estimating expectation values of observables acting on several copies of the quantum state. And that works too. Now, you don't need to know at the time you make the measurements, which are just chosen at random, what properties you're going to want to predict. You can measure first and then ask questions later. And in fact, many of the applications of classical shadows to experimental data that have been done since then have been performed by reanalyzing data that was originally taken with another purpose in mind. Okay, so we have these classical shadows. What sorts of things can we do with them? Well, for good reasons, there's a lot of interest now in using classical machine learning to advance our understanding of many particle quantum systems and material science or chemistry in particular. And in fact, I think an important role for quantum computing in the future is going to be collecting training data in that highly correlated regime about which we don't yet know enough, which can then be turned over to classical ML to predict properties of new materials and chemical compounds. Quantum is going to be important for giving that training data. Well, how well does that work? We can consider this scenario. Suppose there's some smoothly parameterized family of Hamiltonians such that the ground states of all the Hamiltonians in the family are in the same gapped quantum phase of matter, all with a finite, independent of system size gap between the ground state and first excited state energy. And what we can show under mild assumptions is that if we have a local Hamiltonian and we have access to the ground states of some of the Hamiltonians in that family, then we can generalize from measurements on those samples, that training set, to predict properties of other ground states in the same quantum phase of matter. The idea of how it works is that every time we get a state during training, we immediately measure it by that protocol I described, easy measurements, to collect its classical shadow. And then we generalize the classical shadows to obtain a succinct classical description of ground states elsewhere in the phase. So the learning is entirely classical, but we're making use of the quantum platform to prepare the state and to measure the state. So with access to the training data, we can solve problems that would just be too hard to solve if we didn't have access to data from quantum experiments. Another thing we can think about is identifying phases of matter in either a supervised or unsupervised learning scenario. In the supervised case, we imagine, say, there are two different phases of matter, phase A and phase B. During training, we have access to labeled copies of states chosen from either phase A or phase B. And then after training is complete, we receive unlabeled copies, and we're supposed to classify them. Do they belong to phase A or phase B? So we were able to show that this can be done efficiently with an amount of training data and an amount of classical processing that scales reasonably with the system size. And again, the idea is that whenever we get a state, either during the training phase or the test phase, we immediately do the randomized measurement to get its classical shadow. So then the problem becomes classifying the classical shadows, which we can do using standard methods from classical ML. And we could prove that it would really work in an efficient protocol. So there's some classifying function that the machine learning determines, which isn't known in advance, and that can then guide the physicists to give them a better understanding of how the two different phases are distinct from one another. What kind of order parameter can distinguish them? Now, I want to consider the distinction between what I'll call conventional and quantum-enhanced experiments for learning properties. So the setting is kind of similar to what I described before, but now there are these two different types of experiments I want to consider. In a conventional experiment, we get copies of an unknown quantum state one at a time, and we measure them one by one any way we want. The measurements can be adaptive, that is, the measurements we perform on each copy can be conditioned on outcomes of measurements done in earlier rounds. And that's to be, and then after all the measurements are complete, then we're asked to predict some property of the system. That's contrasted with the quantum enhanced scenario where we have a quantum memory. We can deposit copies in quantum memory and then do coherent processing across the copies. So we were able to show that for some tasks, the number of copies that you need, the number of experiments that you need to do to learn a property is exponentially fewer in the quantum enhanced scenario with quantum memory and quantum processing than in the conventional scenario. And furthermore, the entangled measurements that you have to do across the copies in the quantum enhanced scenario are quite simple. So one can do a demonstration, a proof of principle experiment in existing hardware, which we did using 40 qubits in the Google Sycamore processor. So the setting is we had 40 qubits at our disposal. That was enough to store 2 copies of an unknown 20 qubit state. And in the quantum enhanced scenario, we just performed Bell measurements on pairs of qubits, one chosen for each copy. And theoretically, if there were no noise, after all the measurements are complete, we're presented with some observable, which could be a very high weight observable, and we're asked to estimate its expectation value. Or what's really considered here is there are 2 different observables, and we're asked which one has the larger expectation value, so there's a yes-no answer. And because there's noise in the device, the number of experiments we need in the quantum enhanced scenario grows slowly with the system size. Ideally, it wouldn't grow at all. But by the time we get up to 20 qubits, in the conventional scenario, the number of experiments we would have needed to, with high probability of success, answer the question correctly, was 3 orders of magnitude higher. So the vision is that in future quantum sensing platforms, we'll be able to capture data, process it quantumly, and get access to signals that would otherwise be completely elusive. So that's the idea of classical shadows of quantum states. It's a feasible procedure for converting a quantum state to succinct classical data. With only order log m copies and efficient classical processing, we can predict m properties of the system with feasible measurements, as long as the observables don't have very high weight. If we have access to data from quantum experiments, then we can use classical machine learning to solve quantum problems that would be too hard to solve without access to data. And with quantum enhanced experiments, making use of quantum memory and quantum processing, we can have an exponential advantage for some tasks relative to conventional experiments. It's really an exciting time. I took you way back to the beginning when I first got interested in quantum information. I think this is the most exciting time yet because there's so much interaction between theory and experiment. The technology is advancing rapidly, and the theory and experiment are informing one another on a day-to-day basis like never before up to this point. And in the next few years, I think we'll see remarkable progress towards fault-tolerant quantum computing. We saw a significant step in the paper posted yesterday by the Google Quantum AI group. As we heard from Joel Moore, we have the capability now by doing experiments with quantum platforms to study in particular the dynamics of highly entangled systems in ways we never could before, and that enables new discoveries about many qubit systems. And there's a merging going on of many body physics and metrology as we get better at controlling complex states of many particles. We can measure things better, and in particular, that should enable us to get more accurate clocks in the relatively near term. So it's 43 years since Feynman. Quantum computers are interesting now scientifically. They're not yet having a big practical impact on the world. We shouldn't be surprised by that. I mean, what we are aspiring to is enormously ambitious. Fulfilling the potential of quantum information science that we foresee is a grand challenge for the science and technology of this century. We still need extraordinary advances, not just in engineering, but also in basic research to meet those challenges. And that's going to take time. It'll require sustained, inspired effort and investment over decades to come. So it's not going to be fast or easy, but it's going to be impactful and it's going to be a lot of fun. So I hope many of you here will join in the fun and continue to move our subject forward. Thank you.
That was a great talk. Thank you. Most of you are under the impression that I, as the session chairman, are independently in control of the clock, but it's not true. I'm a puppet of the organizers of the conference. So we have a few minutes left. Can I say a couple of questions, and then of course John will be around to answer them as.
That was a very subtle rebuke, wasn't it?
Yeah, go ahead.
So, fascinating talk, thank you. So you talked about using quantum to do better quantum to do better quantum machine learning and so on. Is there any opportunity for us to use quantum mechanical models to actually do training on existing classical data?
Yeah, so the question is, what are the prospects for using quantum processing to improve, say, machine learning tasks with classical data? This is a whole field of research, I don't know the answer for sure, but we don't have a very convincing argument now, in my opinion, that quantum processing is going to give us a big advantage for the types of tasks that we address today with classical machine learning. There's a whole story I won't go into there, but there's been an interesting trend that there have been various proposals for where an advantage might be sought for such tasks using quantum processing. And in many cases, they have wound up being dequantized, meaning it turned out that there were quantum-inspired classical algorithms that could perform the task pretty well. One of the big challenges is that there's an input and output bottleneck. If we're trying to deal, as we often do in machine learning, with very large amounts of data, to load that into a quantum system in such a way that we can get a big speed up is hard to do. That tends to limit the time it takes to do the task. And with the output, we might get the information in total in quantum state, but we can only get a limited amount of information from, say, any shot. I don't know the answer. We'll see.
Can I get one question?
Thank you. Thanks for the great talk. So when you mentioned classical shadows, you mentioned that we can get a classical representation of the quantum data and then use this to gain some properties about, for example, like a quantum state. So I'm wondering if you know if there's like some concrete relation between the complexity of the classical representation and the types of properties that we're able to get from that representation. Like if there's some concrete relation that describes this.
Yeah, so I think the question was, is there some sharp statement we can make about how succinct the classical description is that we use and how many predictions or what types of predictions we can make? I mean, there are information theoretic things you can say, just, you only have a certain amount of classical data. So if you're, trying to distinguish among different quantum states, you can't do any better than distinguishing tasks than is possible information theoretically. But you phrase the question in such a general way that I don't think I have a good answer. We can say more specific things in concrete cases where, you know, I tell you what types of measurements I'm going to make or what type of succinct classical description I acquire. And that was why we were able to make a statement. We needed to have some lower bounds, you know, on the classical processing of the results of quantum measurements in order to say that there was a quantum advantage in the quantum enhanced scenario. And those are also kind of information theoretic, but, you know, they're non-trivial in that we're actually able to show that there are quantum processing procedures that outperform what we can do by classically analyzing the succinct description.
Thank you.
Thank you. Now I really have to ask everybody to thank Professor Preskill. Allow me to introduce the first of the two speakers this afternoon, and that is Nicole Halpern, who is an adjunct assistant professor at the University of Maryland and is part of the Joint Center for Quantum Information and Computer Science at the University of Maryland. She's been here before, which means that we like to hear what she had to say, and so we'll hear again. She's going to talk about quantum thermodynamics for lattice gauge theories, or 10 lessons I learned from John Preskill. So please welcome Nicole Halpern.
Thanks very much to the organizers for the invitation to come speak here and help celebrate John Preskill through the lens of some recent scientific work. If you know John, then you know that one of the best ways to celebrate him is through sharing some of the science that you think is most interesting. So I hope you think this is interesting, and more importantly, I hope John thinks it's somewhat interesting. The one lesson from John Preskill that we've already heard about is that it can be useful to keep a foot in high energy physics and a foot in quantum information theory, as illustrated through his engagement in the black hole information paradox with Stephen Hawking and others. The quantum information theory over the past 15 years has been applied in the growing field of quantum thermodynamics. But what's ordinary thermodynamics? It's the study of energy. Heat, work, engines, and efficiency. It was inspired by the Industrial Revolution. For the first time, steam engines were powering factories, transforming society. So naturally, people wanted to know how efficiently they could operate. But these practical questions led to fundamental questions and insights into, for instance, why time appears to flow in only one direction. Thermodynamics was developed for classical steam engines, large systems. But thermodynamic concepts are still relevant nowadays, and in the very new type of science that we're doing now. We know from quantum information processing that quantum resources such as entanglement can enhance encryption and computation and more. Just as there are these information processing tasks, there are thermodynamic tasks, such as extracting work and charging batteries and cooling systems. So we can similarly ask, how can quantum resources enhance those energy processing tasks? We should also look at the basic laws of thermodynamics and see how they extend to quantum systems, even ones that entangle with each other. Also, we can look at a system that's processing information, energy, and other thermodynamic quantities, and ask, what behaviors can it exhibit only if it's not classical? So we can use thermodynamics to understand better the division between the quantum world and the classical world. So much for quantum information theory in quantum thermodynamics. What about high energy physics? So I am going to define high energy physics like a European. I am told that Europeans include nuclear physics and high energy physics. I recently fell into the orbit of the group of Zora Davuti at the University of Maryland. She is in nuclear physics, a little bit in high energy physics. And she and her group told me that there are some remaining problems, thermodynamic problems, with gauge theories. So I should provide some background about what gauge theories are. These are models that are prevalent across many fields, including high energy nuclear physics and condensed matter. One example that we're all familiar with is electrodynamics. A gauge theory is a model that has a local symmetry. It has more degrees of freedom than the actual physical system that is being described. And these extra degrees of freedom are related to this local symmetry. For instance, quantum electrodynamics has a U1 symmetry. An important part of gauge theories consists of Gauss's law. Gauss's law is a constraint that's imposed locally, and it interrelates matter over here with the gauge theory, with the gauge field that is around that matter. For example, suppose in electrodynamics that we have a charge at this point, and we have an electric field around that charge. According to Gauss's law, if we look at a surface that encloses the charge, we take this surface integral with the gauge field, then we find it's proportional to the amount of matter inside, the amount of charge inside. So the charge here is related to the gauge field around it. Now, what about quantum gauge theories and lattice gauge theories? The lattice gauge theory has discretized spatial degrees of freedom. The matter lives on the sites. I'll index these with n. And the gauge field lives on the links between the sites. How does Gauss's law manifest in this quantum setting? Well, the whole system is governed by some Hamiltonian. And there are operators, Gauss law operators, Gn, associated with the sites n, that are conserved by the Hamiltonian. And our whole system has a very, very large Hilbert space, but only a subspace of it consists of physical states that are really accessible to the physical system of interest. These physical states are states psi-physical, such that if you act with any Gauss law operator on a physical state, you'll find it's an eigenstate associated with some fixed eigenvalue, little g. If we're talking about a gauge theory in the standard model of particle physics, then the value of this little g is given to us by nature. These states are very highly entangled, and relatedly, Gauss's law implies that if you look at the site degree of freedom over here, it is very much dependent on the gauge field around it, which in turn is dependent on the matter sites a little farther out, which are dependent on the gauge field even farther out. And so everything is interdependent on everything else. So how can we do what thermodynamicists like to do? Say that there's some independent degrees of freedom over here, I'll call them the system of interest. There's some independent degrees of freedom over here, I'll call them the environment. And I'll say that energy exchanged by system and environment is heat. How do we define heat? And accordingly, how do we define work for lattice gauge theories, where there's just this big mess of interdependent degrees of freedom? Or a bigger question is, how can we define quantum thermodynamics for lattice gauge theories? This question should matter to us because thermodynamics is something of the queen of the physical theories. It governs the other physical theories. So if we have lattice gauge theories, it's just that we don't know how to formulate thermodynamics within them, we should be troubled. And why should we care about this question in this conference? In part because one of the attractive possible applications of quantum simulators and quantum computers is, as John alluded to simulate lattice gauge theories, do some of our tough calculations. I had the privilege and pleasure of working with a wonderful team of people on addressing these questions to an extent. Now, lesson number 2 from John is to live tweet the talks you attend. As far as I know, he might have been the first person who became known in quantum information theory for doing this. And if you have not live tweeted this talk yet, this would be a great point to do so. As has already been pointed out, John has a very impressive Twitter following. I'm a millennial. Social media supposedly took off with my generation, but I like being able to say that my PhD advisor is far more popular on social media than I am. So, Zora Davuti is a faculty member at the University of Maryland. So is Chris Jarzinski, he's a thermodynamicist. Nicholas Mueller was a postdoc in Maryland. Now he's taking on a faculty position. Grishma Oroganti is a PhD student with Chris. Connor Powers is a PhD student with Zora. And I'm really grateful to this wonderful team. So here's where I'd like to go in the rest of this talk. I'll introduce you to a toolkit from quantum thermodynamics, strong coupling quantum thermodynamics. And then I'll introduce a protocol that we can perform on quantum simulators to simulate lattice gauge theories. Then I'll use that toolkit to define the work and heat exchanged within this lattice gauge theory protocol. And I'll show in an example of a Z2 lattice gauge theory that these quantum thermodynamic quantities that we define, the work and heat, can be useful for understanding some qualitative behaviors, namely they evidence a phase transition. Then I'll talk about opportunities for future work. The lesson number 3 from John is be willing to change where you're going if someone has a better idea from you. And I've seen him say multiple times when he's received criticism, well, what would you rather do instead? What are other strategies? So someone who had a better idea than I did when I started on this project was the people who developed strong coupling thermodynamics. I was not one of those people. I had heard of this toolkit and thought it sounded maybe useful for lattice gauge theories. So someone who has helped develop the strong coupling toolkits was my collaborator, Chris Jarzinski. Since I'm at the University of Toronto, I should point out that Devira Siegel's group has done a lot of work in this field, and so have other groups across the world and across time. To understand strong coupling quantum thermodynamics, we should start with weak coupling quantum thermodynamics, mentioned in Ronnie Koslov's talk earlier. This is the setting that we usually assume holds. Here, we think about a system of interest interacting with some big reservoir. The two will exchange heats, and maybe work is performed as well. We attribute to the system reservoir composite this Hamiltonian with a system piece, a reservoir piece, and a coupling. A natural definition for the average total internal energy is the expectation value of the total Hamiltonian. And we assume that this coupling contributes negligibly to this total internal energy. Why should we do that? Well, in many cases, this system and reservoir interact just through the boundary that they share. And this boundary is of some size according to your favorite matrix norm. That's like the boundary of the system of interest. In contrast, the magnitude of the Hamiltonian of the system of interest is like the volume of the system of interest. And if S is of a decent size, the volume is going to be much larger than the boundary. This situation leads to an intuitive definition of the average system of interest internal energy, the expectation value of just the system Hamiltonian. And it is very common for us to believe that if the reservoir is in thermal equilibrium at some inverse temperature, then the system will probably end up in a thermal state at that inverse temperature. However, if the system of interest is small, maybe quantum, then the volume might not be so much larger than the boundary. These quantities might be comparable, and our usual assumptions break down. It's difficult to figure out how much of this coupling energy we should attribute to the system, how much we should attribute to the reservoir, and so how we can define, say, the heat that the two exchange. So we need strong coupling quantum thermodynamics. I did not create this figure for this talk. It already existed online. So you can blame them. So here's the strategy we're going to use. We're going to posit definitions of useful energetic quantities, often via analogy with the weak coupling case. And then we're going to show that our posited definitions are useful, they're reasonable because they obey the first and second laws of thermodynamics. So now suppose we have our system and our reservoir, and we suppose that the whole thing begins in a Gibbs state. Why should we do that? There are a couple of reasons we might want to. First, the system reservoir composite might be coupled weakly to an even bigger bath out there at some fixed temperature. And second, if the system and reservoir composite instead forms a closed isolated system, then in many cases we might expect it to reach a microcanonical state. If the global system is large enough, then predictions we make with the microcanonical states are very close to predictions we make with the canonical state. So we can't distinguish the two, and let's just say the whole thing is in a canonical state. And the system's reduced state follows from tracing out the reservoir. And we can write this reduced state in a form that looks thermal, as long as we define this HS star in a certain way. We call it the Hamiltonian of mean force, and it's the negative of 1 over the inverse temperature of the log of this ratio. Now, that definition looks rather artificial, but if the coupling is weak, then this formula really just reduces to the ordinary system of interest Hamiltonian. And we showed in our paper that this Hamiltonian of mean force, which is very much used in strong coupling quantum thermodynamics, is very closely related to the entanglement Hamiltonian, which is used in quantum information and many-body physics. I don't have time to show you details, but feel free to ask later. And this ZS star acts like a partition function. It normalizes the state. We can now positive an intuitive definition for the average system internal energy, the expectation value of the Hamiltonian of mean force. It naturally incorporates some of the influence of the strong coupling. We can also introduce free energy type quantity. Let's notate by W the work absorbed by the system of interest during our favorite process, and denote by Q the heat absorbed. So lesson number 4 from John is always to keep an eye on the basic physics. This image comes from a blog post by a former group member who said that whenever John was explaining some complicated physics concept, he used very basic ideas in this very kind of lulling and melodious voice, like a snake charmer's voice, that would charm everyone around into going back to their textbooks and reading about basic physics. But what is more basic than energy conservation? The first law of thermodynamics. After that comes the second law of thermodynamics. So the work that we need to do in order to change the Hamiltonian in a certain way is at least the difference between the free energies of the equilibrium states associated with the initial and final Hamiltonians. That's all very well and good. It's the notation of thermodynamics that we know from classes, but in the context of strong coupling, how should we define work and heat? Well, the answer depends on what thermodynamic protocol we're performing. So we need to choose a protocol, and we picked a protocol following essentially 2 principles from John. One is to know your math, be a good theorist. The other is not to piss off your experimentalist friends. So Tom Rosenbaum is a quantum experimentalist at Caltech. We don't want to ask our experimentalist friends to try to do things that are basically impossible for them to do. Now, Tom also happens to be the president of Caltech, so I guess John has multiple reasons not to piss him off. So we decided to study a sudden quench process. This is an instantaneous change of the Hamiltonian, and it's been performed with lots of quantum simulators. In our setup of interest, we'll have some degrees of freedom. Some will call the system, some will call the reservoir. The whole Hamiltonian is like the one we just saw, except the system of interest Hamiltonian can change in time. This quench protocol has 3 steps. During the preparation procedure, up until time t equals 0, we have the global Hamiltonian equal to its initial value, so the system of interest Hamiltonian has its initial value. We start off the whole system in a global thermal state, and of course the system of interest reduced state follows from tracing out the reservoir. The quench happens at time t equals 0. So we change the Hamiltonian very quickly, that is the Hamiltonian of the system of interest, and by implication, the global Hamiltonian. And this quench is so quick that the state does not have time to change during that quench. During the final step, we let the whole system re-equilibrate. So the whole system ends up back in a thermal state just with respect to the final Hamiltonian. And once again, the system of interest state follows from tracing out the reservoir. Great, we have our protocol. Now how do we define the work and heat exchange during it? Again, we want to keep our experimentalist friends happy, so let's ask them only ever to measure the small system of interest. Because it's small, the reservoir is usually a large system with a bunch of degrees of freedom we don't have control over. How do we define the average work? In general, work is controlled energy that can be doing something useful like powering a factory. It comes from controllably tuning some parameter in the Hamiltonian. That Hamiltonian change happens at time 0 during the quench. So we define our average work in terms of the final Hamiltonian minus the initial Hamiltonian and the state that does not have time to change during the quench. We can also define the average dissipated work. This delta Fs, at least in the classical case, is the minimal amount of work that we would need to invest in order to change the Hamiltonian in this way. But if we're kind of lazy, we might perform some extra work we didn't have to, and that work gets eventually dissipated to the bath. This dissipated work is a useful quantity to consider because we expect it to be experimentally measurable because of that connection we found between the Hamiltonian of mean force from strong coupling quantum thermodynamics and the entanglement Hamiltonian from many-body physics and quantum information. This relationship that I have not shown you because I haven't had time. How do we define the heat absorbed by the system of interest? Well, heat is energy exchanged with a thermal reservoir. And the system has time to exchange heat with a thermal reservoir just in the last step of our protocol. In the last step of the protocol, the Hamiltonian is fixed, but the system of interest state changes. We showed that these definitions of work and heat are, we think, kind of reasonable because they obey the first and second laws of thermodynamics. Lesson number 7 from John is to be a two-trick pony. So he wrote a blog post in which he said that a lot of physicists are one-trick ponies. They know one field extremely deeply, extremely well, but it could be more fun sometimes to be a two-trick pony and know about 2 fields, because then you can use insights from one field to inform the other field. So let's be two-trick ponies and see that lattice gauge theories are really nothing more than strongly coupled quantum thermodynamic systems, even though at the beginning of the talk we said how to define their quantum thermodynamics is really unclear. So remember Gauss's law? It has these Gn Gauss law operators. We can, particularly in a quantum simulation, effect or implement Gauss's law by seeing it as effectively adding a penalty term to the Hamiltonian. Lots of people have written a lot about this strategy. See our paper for lots of references. So you take the lattice gauge theory Hamiltonian and add on this term. This F is a function of the Gauss law operators. And remember, the Gauss law operators take matter at some sites and couple it to the gauge field nearby. Therefore, this Gauss law term will contribute to our coupling term in our thermodynamic Hamiltonian. Furthermore, in order for this penalty term to really penalize transitions outside of the physical subspace, this term needs to be big. And so we can see it as contributing to strong coupling. So the takeaway so far is that we can see a lattice gauge theory system in 2 ways. Either it's this hopelessly interdependent mess of degrees of freedom, if we don't think of Gauss's law as a penalty term in the Hamiltonian, or we can stick the Gauss law into the Hamiltonian and see the lattice gauge theory as really having a system and a reservoir that are just coupled strongly in a quantum thermodynamic sense. So lattice gauge theories fit into the paradigm of strong coupling quantum thermodynamics. And so by being two-trick ponies, we can use strong coupling quantum thermodynamics to define the work and heat exchanged within a lattice gauge theory. I'll illustrate how that's done with an example that was simulated numerically by Connor of a Z2 lattice gauge theory. We thought about a one-dimensional system. The matter consisted of hardcore bosons. These lived at the sites indexed by little n, and there are big N sites total. We attribute to the matter Pauli operators sigma alpha n. The gauge field also consists of hardcore bosons. These live on the links, and we attribute to them Pauli operators tilde sigma. Because we're theorists doing numerics, we had periodic boundary conditions. And this model was adopted from a model with fermions, so you're going to see some artifacts of that when I say things like chiral. Our Hamiltonian has a bunch of terms. One is the strength of the electric field, the gauge field. So this epsilon is the electric field strength. Tilde sigma x is the electric field operator. There's a hopping term. So as matter hops from site n+1 to site n, it has to hop through this gauge link, and as it does so, it takes the electric field and flips it around, the z-axis. This J is the hopping frequency. There's a mass term. This -1 is here. It's called a staggering. It's here only because we took a model that originally had fermions in it. There's a chemical potential term for the mass, and then there's a term you can forget about. It's just a constant. It's there for numerical stability in the simulations. What do the Gauss law operators look like? Remember, a Gauss law operator acts non-trivially on a site n and on the surrounding gauge links. You can mostly think of it as an XX. In the absence of any matter, this exponential just equals ±1. So you can really think of the Gauss law operator as just an XX, which generates a Z2, a flipping symmetry. We can put that Gauss's law operator into the Hamiltonian in the form of this penalty term. So this is our F function. And this is the strength. These are the terms that you've already seen in the Hamiltonian. What's our quench protocol? We're going to take the chemical potential for the matter sites. They all start at 0. And then at time t equals 0, we quench the chemical potential of the sites within the system of interest to some larger value, mu f. Now, I have to partition my system of interest and my Hamiltonian in the thermodynamic way into a system of interest, which I'll color purple, and a reservoir, which I'll color blue. We have a hopping term and a Gauss law term. These are they have some coupling terms within them. Some terms act on the system of interest alone. Those go in the system Hamiltonian. We can say something similar about the reservoir, but there are these terms that act on the system and reservoir together. These are couplings. We have an electric field term. This is more straightforward. Some subterms act on the system of interest. Those go in the system Hamiltonian. Now, this is actually, this is a trickier, more subtle effect. There are some electric field terms that act on a gauge link that isn't in the reservoir, but it touches the system of interest. And we're going to say that those belong to the coupling, and then argue ultimately that this is a good choice. And all of the other terms should belong to the reservoir Hamiltonian. The final two terms we need to care about have some terms that act just on the system. These go in the system Hamiltonian. Some terms that act on just the reservoir. These go in the reservoir Hamiltonian. And again, don't worry about this constant. Now, our model has two different phases. The order parameter is called the chiral condensate, again, because this model was derived from a fermion model. We call it sigma. So this NS is a normalization factor. It's the number of the sites in the system of interest. This expectation value is the amount of matter on a particular site, and it's evaluated in the thermal state. And this -1 is here, again, because of the fermion earlier theory. The phase is controlled by the chemical potential term in the Hamiltonian. Suppose that the chemical potential within the system of interest is really large, then because of this negative sign, the matter sites are going to want to align with each other. Namely, they're all going to want to be populated. So this is going to be 1 for all of the little n's. But because we have this negative sign here, our order parameter is going to be like +1, -1, +1, -1. It's going to end up being 0. We say that this is the chiral phase. In contrast, if the chemical potential is small, then our order parameter can be finite. We say this is the symmetry broken phase. So takeaway, we have two phases. Now, we used in our simulations parameters from order 1 to order 10. Here are the particular values in case you're interested. And under these conditions, the transition happens when we quench the chemical potential to about 1.82. Okay, here are the results. I'm going to show a plot. On the x-axis is the final value of the chemical potential in the system of interest. On the y-axis is the amount of work dissipated by the system according to our posited definitions during the quench protocol. Here are the results. This gray line shows the phase transition at about 1.82. And we can see that this dissipated work changes very noticeably about the phase transition. you can put together a similar plot for the heat that is measured according to our definitions. So in summary, if you use strong coupling quantum thermodynamics to define the work and heat exchanged within a lattice gauge theory, then these thermodynamic quantities will signal a phase transition, or an expected phase transition, because these are finite-sized numerics. Lesson 8 from John is to think big. So what do we dream of for the future? Well, we'd like for experimentalists to undertake this protocol and start measuring the work and heat exchanged within lattice gauge theories. We need to generalize to other protocols, like can we define the work and heat exchange during particle scattering, for instance, and what can it tell us? Can we detect other phase transitions, like topological phase transitions, using work and heat? And more broadly, we'd like to develop quantum thermodynamics of lattice gauge theories. Lesson number 9 from John is always do what excites you most. I, a few years ago, was not expecting to work on lattice gauge theories, but I do think this intersection, this two-trick pony idea of bringing together strong coupling, quantum thermodynamics, and lattice gauge theories is pretty exciting. There's a lot to do. So if you're interested, feel free to talk to me later. In summary, we reviewed the toolkit of strong coupling quantum thermodynamics, which comes from one field, which has been inspired by quantum information over the past 15 years. We proposed a protocol that we can perform on quantum simulators for simulating how lattice gauge theories behave during a quench, hopefully not upsetting our experimental friends too much. As two-trick ponies, we used that toolkit to define the work and heat exchange during that protocol. We looked at an example with a Z2 lattice gauge theory and saw that our thermodynamic quantities can evidence a phase transition if defined according to our toolkit. Finally, we saw that there is still a lot to be done. I was fortunate enough to be a grad student still at Caltech during one entangled evening, which was part of the celebration of Richard Feynman's 100th birthday. So I got to see John sing and dance on stage. Since lesson 10 is don't be afraid to embarrass yourself, I think that this is a great time to invite questions.
Yeah, thank you very much, Nicole. So I might have missed how you define work. So is that you're suggesting a 2-point measurement of the expectation value of the energy, or it's based on some ancilla that is coupled to the system?
Yes, okay, so the question is about how we define work and how we measure work. And I think you're probably referring to how a lot of quantum thermodynamic protocols involve this 2-point measurement scheme, measure energy at this point, measure energy at that point. I appreciate that many body Hamiltonians are very difficult to measure. So our scheme relies on measuring the entanglement Hamiltonian, and because of the connection, whose math I did not have time to show you. And so the entanglement Hamiltonian has been experimentally measured in some cases when it is well described by a certain parameterized ansatz. And we expect that entanglement Hamiltonians in these thermal states will also satisfy a simple parameterized ansatz. That's one of the things that we're checking next. And so the idea would be to use entanglement Hamiltonian tomography to infer the entanglement Hamiltonian, and so infer this expectation value of the Hamiltonian of mean force.
That was pretty amazing. This idea of being able to define work and heat for lattice gauge theory is fascinating and conceptually satisfying, but does it also offer us new insight? Like, what kind of new results does it enable us to have?
We were surprised to see this phase transition come out of the dissipated work. So that's one example that we have now. It is just one example, and that's why some other work that we're planning is to try to detect other types of phase transitions, like topological ones, through work and heat, and yeah, see what other large-scale qualitative phenomena we can find.
Thanks for the nice talk, Nicole. Like, as you know, kind of well, I guess, you know, that dissipated work and work statistics have been kind of extensively explored in sort of quenches in second order standard kind of quantum phase transitions, you know, and they uncover kind of universal scaling, etc. And I haven't seen this done in a strongly coupled kind of scenario, so that's interesting for me. But so, one of the cool things about the closed system scenario is that the dissipated work can be written as a quantum relative entropy between the pre and post quench states. I mean, is there a way to do this for the strongly coupled case, or have you explored something like that? Because, you know, it kind of gives you something like a divergence measure that you can think about the thing geometrically.
And I also would like to say that as we were putting together this project, we were looking at some of your work, which was some of the inspiration for this. So about writing dissipated work as a relative entropy, let's see, I know that we were using relative entropies and then the data processing inequality in our proofs of, some of the proofs of the second law of thermodynamics. But as for using it in the analysis, we haven't tried doing that.
Let me try a question. I'm just curious about those terms that you suggested we don't worry about, the ones that stabilize the system. What is the physical meaning of those terms, and how do they impact your calculations?
So it was really Connor who came up with this idea of adding terms onto the Hamiltonian to ensure that HS and HR and the coupling do not have negative eigenvalues, because he was doing a lot of calculations of e to the negative beta h. And if the total Hamiltonian were to have negative eigenvalues, e to the negative beta h could end up being like e to the really big positive number, and that led to instabilities. And the goal was to avoid those instabilities.
Does it have a physical meaning?
No. It's just an energy shift of the overall Hamiltonian.
More questions, please?
One more question here. Okay. Well, thank you for the talk. It's very interesting. And perhaps I'm taking lesson 10 to heart because I'm asking this really knowing nothing about lattice gauge theories. But since you mentioned like it's a hard boson model, I'm wondering if you were like to do something analogous to Jordan-Wigner transform, and you went from a spin picture to fermion picture, or vice versa, like do these work and heat look the same, and do they have a similar physical meaning, or would you get like different insights by switching to that picture?
We were, as I wrote, using Pauli operators, so effectively using just qubit systems. I mentioned that this model was adopted from a fermionic model. As to why it was our lattice gauge theory collaborators who suggested using this particular model. As to why they suggested this particular model, I think it was because of calculability and convenience of the numerics. But one thing that we very much want to do next is try a number of other models.
So let me ask you to thank Professor Halpern for a really great talk. We seem to be moving PhD lives forward and backward in time. First we had Nicole, who is
Sorry, hold on just a second here. Okay, thanks. Thanks to the organizers for inviting me. It's really an honor to be here for celebrating John's award of the Bell Prize. So Paul, you may not have a bell, but we do have a Bell Prize at least. And also I want to thank you, Paul, for explaining exactly what John's award is for out of all the many great things that he's done, because we would definitely, in this case, not want there to be any hidden variables. Okay, so what I want to talk about today is a topic that John and I have both worked on quite a lot, together and separately, which is fault-tolerant quantum computing. And in particular, I'm going to talk about a new direction that I'm kind of excited about, fault tolerance with dynamical codes. So this is kind of explained in a paper that I had on the archive a couple of years ago, and a little bit of further work with my student Xiaozhen. So just to make sure that we're all on the same page, what do I mean by fault tolerance? Well, so I think we understand that to build a really big quantum computer and one that's reliable, we're going to need some way of dealing with errors. And so the standard way of doing that is to take your qubits and encode them using an error-correcting code. So you have extra qubits. There's some constraints on what those qubits are supposed to be. If those constraints are violated, you can tell that there's been a change and that there's been an error. And so that's what the error-correcting code does. But the error-correcting code by itself is only really useful for communication. Alice is sending qubits to Bob. Alice and Bob have perfect quantum computers, but the channel between them is imperfect. We know that's not realistic. If we want to build a big quantum computer, we have to deal with the fact that there's errors in the computation itself. And so that's what fault tolerance is. Fault-tolerant protocol is something we put on top of an error-correcting code, some additional procedures we follow in order to do gates, to do error correction, to encode and decode, all while everything that we do is imperfect itself and has additional errors. And so we know that there's a threshold for fault tolerance, so that if you can get the error rate below some magical constant value, the threshold value, so if your error rate per gate and per time step is below this threshold, then we can apply this software idea of fault tolerance to make arbitrarily large quantum computations arbitrarily reliable. And so, if the error rate is low enough, then basically we can correct the errors faster than they occur, and we can make the logical state arbitrarily good. If the error rate is higher than the threshold, then they accumulate faster than we're able to correct them, because everything that we do to try to correct them is introducing more errors. And so it's a very important question of, what is that value of the threshold? And the reason that there's big companies working on fault tolerance is because it doesn't seem to be that bad. It's not easy. We're only kind of just reaching that, but it's achievable. And so the lower bound on the threshold, meaning we want the threshold to be high, right? So a lower bound is the best we know how to do right now, is due to an old protocol by Manny-Nil, which showed, depending on the error model, an error rate of about 3%. You could do fault tolerance below that. Now, that protocol is not practical at all. It requires, millions of extra qubits or something. But even a little bit below that, we start to see actual practical protocols. But it's an interesting question to ask, can we do better? And, well, we don't know how to do better. This is the best we know how to do right now. But you can say, is there an upper bound on the threshold? What is the best we could possibly do? And the thing is that the upper bound on the threshold that we have right now is only about 45% error rate, which is actually ridiculously high. That's higher than we can even do error correction. And we know we can't do error correction that high. Maybe there's some crazy way of doing fault tolerance without error correction we don't know about. So that's probably not achievable. But my point is that there's a big range between what we know how to do and where we know that it doesn't work anymore. So there's room, potentially, theoretically speaking, for improvement. Another factor about fault tolerance is that usually they require a lot of extra qubits. which we don't really like because we'd like to build the smallest quantum computer and get the most bang for a buck that we can. The threshold we want it to be high, the overhead we want to be low. So the upper bound on the threshold is kind of what we can do now. And even with the best protocols nowadays, it's still a factor of 20 more physical qubits than logical qubits, probably more than that in practice. But what's the lower bound? What's the best that's conceivably achievable? And well, in theory, in the asymptotic limit of very many qubits, it is possible to have that overhead ratio, physical qubits to logical qubits, be arbitrarily close to 1. Okay? Again, that's not something that's likely achievable in a real physical system, but the point is that there's room for improvement. Okay? And so how can we improve, right? I mean, can we get closer to those to the non-achievable bounds? Probably not. I mean, probably we can get closer. Maybe we can get closer, but we can't get all the way up to them. Probably the upper bound on the threshold and the lower bound. Well, the lower bound on the overhead is actually a theoretically achievable lower bound, not practically achievable. But the upper bound on the threshold probably isn't. Probably we can't do that well. But we may be able to improve beyond what we have now. And so how to do that? Well, I think that to do that, we're going to need some new ideas in fault tolerance. We can't use just the existing protocols and tweak them a little bit. That's going to continue to produce improvements, and those improvements might be very valuable. But if we want a big improvement, we've got to look elsewhere. And there's actually a whole scope of potential fault-tolerant protocols out there that have not really been investigated. And so that's what I want to talk about today. So let me start by calling back to work from John that was not in the prize citation because it was too old. So this was a paper written by John with me and Panos Alaferis. When I say written by John, I mean exactly that, written by John. Panos and I helped with the science, but at least back then, and maybe still today, if John writes a paper, he writes the paper, because that's the only way to achieve his standard of exposition. I don't know how he does that. I have trouble, finding time even to read the papers written by my collaborators, let alone write them. But yeah, even back then that was a problem. It's much worse now. Anyway, okay. So here's a little excerpt from that paper. It's a fairly long paper, but I just want to focus on one little thing, which is in that paper we address the question of what does it mean for a protocol to be fault tolerant. Okay, and so here are two properties selected out of a list of about 6 or 7. And so what these two properties say is what it means for a gate gadget, a way of fault tolerantly implementing a gate, to actually be fault tolerant. And there's two basic concepts behind the properties. I'm not going to explain all the notation here, but property 2 basically says that errors cannot propagate badly. That if you have a system, you do a fault tolerant gate, and there's some errors going into the gate that are already there from the earlier computation, and that's S errors, and you add R new errors during the gate, then the total number of errors that come out of the gate should be R plus S errors, right? And maybe that seems obvious, but it's not obvious at all, because if you do gates, they can cause errors to propagate, to spread from one qubit to another. And so if you're not careful about how you do your gates, the number of errors that come out of your gate gadget is larger, maybe much larger, than the number of errors that started there and that occurred during the gate. Okay? But by designing your gates carefully, you can ensure that there's not too many errors per block of the code, and the number of errors stays under control. You can still correct them. Okay? So that's a very important property for fault tolerance, or at least so we thought. And so then property 3 is a little more obvious. It just says the fault-tolerant gate should do what you think it does, right? That if it's a Hadamard, logical Hadamard gate, it should do the Hadamard on the logical qubit. And property 3 is just a way of formalizing that. Okay, so these were conditions that, I mean, since the paper by Peter Shor that John mentioned, creating the field of fault tolerance back in 1996, these are the conditions, were formalizations of conditions that intuitively we all understood as necessary for fault tolerance. But actually, they're not necessary. There are sufficient conditions for fault tolerance. But I think there's stuff that goes beyond this. Property 3 is probably pretty good, but property 2 in particular, we can do better than that, maybe. So, so to explain this new idea, there's a lot of work that kind of points to it and points to other ways of thinking about fault-tolerant protocols. And so let me select out 4 of them and introduce them to you, and then I can kind of explain from them what this new idea is. So, so in particular, let's start with the idea of flag fault tolerance. So this was developed as a way of being more efficient with qubits and fault-tolerant computation. But it's very interesting because it breaks this idea that errors shouldn't propagate. So in a regular fault-tolerant protocol, you design your gates so that, you know, if you have one error, say in the middle of a measurement, like on the left there, that it should not spread into more than 1 qubit of your code block, okay? But the circuit on the left has a property that if there's an error that occurs kind of in the middle of it, it will spread to 2 qubits, okay? So that's not a fault-tolerant circuit. And there's traditional ways to fix that using cat states and lots of extra qubits. Flag fault tolerance says instead, you know what? Let's let it spread into the code block, but let's monitor it so that if there happens to be an error in that one bad place that causes, you know, error propagation, bad error propagation, we can see that there's been an error. We have some extra information beyond what we're measuring for the error correction. And that extra information, this flag, will let us see that this bad error has occurred. And then once we know that, we know how to deal with it. Okay? So the lesson you should take from this, and from flag fault tolerance in general, is that error propagation doesn't have to kill us. That if we can keep track of it and identify when the errors occurred, as well as where they occurred, then we can still do fault-tolerant computation. Okay, so the next thing is actually not just one work, but a lot of papers that work on the idea of code deformation. So code deformation is one of those ideas that's been out there for quite a while as a way of doing fault-tolerant gates, and it's pretty well accepted. So one example of how code deformation works is in the surface code. Maybe you're encoding your logical qubits using pairs of defects, big holes in your surface. And you can do gates in that case by moving these holes around. And when you move the holes around, that means you're actually changing the code, right? You have one specific code where the holes are here. When the holes are here, that's a different code, formally speaking. It's a related code, but a different one. When they're here, it's different again. And as they keep on moving, that's a whole sequence of different codes that you're moving through. Eventually, you get back to your original code. Your holes are back in the original position. And what you can see is that the state, the logical state of the code has changed from before you moved them. So by moving through this sequence of codes, you've changed the logical state. You've done a logical gate. And if you're moving them appropriately, you've done this in a fault-tolerant way. Okay? And so actually, this example is for surface codes. It sounds kind of topological. But actually, you can think of pretty much all gates, logical gates that we have, as some sort of code deformation process. And some of them are topological even when they don't seem that way, but that's a separate story. So, so the thing is that this is telling us that we shouldn't just think of the first error correcting code we have, right? Traditionally we say we're going to do error correction with this particular code, and then the fault tolerance works around that. But as we see in the example of code deformation, thinking about other codes can help us. And so then there's a more recent work of Floquet codes. And Floquet codes take this a step further and say, well, you know what? If we're going to be switching between different codes, why do we have to pick one of them as being the code, right? So in the example of Floquet codes, they have a sequence of 3 codes. And they constantly switch between these 3 codes in a cycle. And none of them is the code. Collectively, they form the encoding. And so the specific example of the first locate code, the honeycomb code by Hastings and Ha, they saw an advantage for this because then they only had to make 2-qubit measurements and still achieve something that's very similar to the surface code. Whereas the surface code requires 4-qubit measurements in order to make it work. So, so there's definitely some advantage to be gained by this. But the main lesson that I want you to get out of this is a conceptual one, which is that it's okay if the code that you're using, the quantum error correcting code you're using, changes over time. And you don't have to have a specific code that's your favorite code that you always go back to. Instead, you could have a bunch of codes that are kind of on a more equal footing. Okay, so the next work that I want to mention is by Nickerson and Bombine. So they were working for PsiQuantum. PsiQuantum, of course, does optical quantum computing using measurement-based quantum computation, which is a good match for photonic, what you can do with photons. And so they're interested in measurement-based quantum computing. They still need fault tolerance. In particular, they're interested in erasure errors, but that's not too material to this discussion. But what they found was, so normally with measurement-based quantum computation, what you do is you take a circuit and you convert it into a measurement pattern. And you say, okay, well, we have gates at time 1. That means we do these measurements on this big entangled state. And then at time 2, we do this sequence of measurements on the next set of qubits. And then this set of measurements for time 3, and so on. And so that's a time foliation of this measurement computation. But the funny thing is that if you're doing just Clifford group gates, if you're just doing the gates that you need for most error correction procedures, stabilizer-based error correction procedures, it doesn't actually matter what order you do these measurements in. You can do them all simultaneously. Okay? And they said, well, okay, if we're doing them all simultaneously anyway, if the order doesn't matter, why do we have to even have this breakdown into time 1 and time 2 and time 3 and time 4? Let's look at measurement patterns that don't have a natural way of breaking them down into different time steps, different time slices. And when they did that, they found cluster states, entangled states, and measurement patterns that performed better for their specific task of erasure correction. And so while that's in the measurement-based model, I think there's still an important lesson that we can draw here, particularly viewing in the light of the previous lessons that I mentioned, which is that it's a good thing to look at a fault-tolerant protocol as something in space and time, right? And we shouldn't treat them separately. We should really treat them together. That looking at them together can actually give us improvements and give us new insights into how these fault-tolerant protocols work. Okay. So let's do that. Well, let's try to do that. So when we do that, what do we want? So we have some system where the code might change in time. And what we'd like to do, remember, if we're giving up on error propagation or controlling error propagation, what we'd like to do instead is identify when and where errors occurred. So can we do that, right? The existing protocols don't. Even flag protocols only identify certain particular errors when they occurred. But maybe it's possible to come up with a fault-tolerant protocol where we know for every fault that happens in the system, every gate that goes wrong, exactly which gate it was. And when I say which gate it was, I mean both when it occurred and which qubits it occurred on. So is that possible? Well, I don't know the answer to that. What I do know is that we can study this by just seeing if there's enough information available to us to potentially figure this out. And so how do we do that? That's a relatively straightforward calculation. So if we have a system with n logical qubits plus m extra qubits, which are kind of you're making m measurements basically in one kind of error correction cycle. And this error correction cycle contains a total of t gates. Then you can calculate how many different possible errors there are, right? If the error rate is p per gate, then you expect there to be about p times t errors. And they could be distributed any way among these t different gates. And so if you count that, you say, take the log of it, you say, how many bits of information do I need to actually even specify what the error was? Well, it turns out to be T times H of P plus P log A. H of P is this binary entropy, minus P log P minus 1 minus P log 1 minus P. Okay, so if we need to specify that amount of information, then how much information do we have available? Is it more than that or less than that? Well, we're making m measurements. So we're getting a total of m bits of information. Okay, so if m is greater than that, then, well, at least we have enough information. It doesn't mean it's the right information, but it's at least possible. If m is less than that, then that means there's no way we can possibly exactly identify what the error was. So, so if the whole circuit, this error correction part of the circuit takes a time d, so it has depth d, well, then the total number of gates is at most d times n plus m, right? T is that. And so that means that t is already going to be linear in m, but it's also proportional to d times m. So if d is a constant, then at least for small enough p, it's possible that we have enough information because t is proportional to m, the number of measurements we're making. If d is greater than constant in m, then we don't possibly there's no way we can have enough information. So, so constant d is not unreasonable. It's something that you might be able to achieve, and you might therefore be able to design a circuit that has this property. Okay, so what we want to do then is we want to think of the fault-tolerant protocol as a space-time code. So it's a code that extends over space and time, and faults occur at gates that occur at some space-time coordinate, and our goal is to identify what those space-time coordinates are. Okay, and that's a little like what an ordinary error-correcting code does, right? An error-correcting code has errors in space, and you're supposed to identify where those errors are in space. So now we're just extending time and treating them on an equal basis. So, here's a variety of questions you might ask about that. So one of them is, well, we have these existing protocols. Some of them, the error correction circuits, probably most of them, don't have constant depth, right? As you scale up to bigger and bigger protocols, the depth of the protocol for making ancillas and stuff like that, the measurements you make, that increases with the size of the system. And so the answer to that is, well, the reason we can get around that is because we made these rules about error propagation, right? If we say the errors don't propagate between qubits in the code, then that means we don't need to know exactly when they occurred. It doesn't matter if there's an error at time 1 or an error at time 3. They'll both produce an error on qubit 3, and we can correct them in the same way. So in the terminology of regular quantum error correction, these are kind of degenerate codes. And what I'm saying is that if we lift that constraint and let the errors propagate willy-nilly, then we have to be more careful to find out exactly what time it is. So that's an advantage that the existing protocols have, but maybe we can, despite not having that advantage, maybe we can still do better by allowing this more wider variety of protocols. Okay, so another question you might ask is, well, if we just do some quantum circuit that's getting this information, what actually is the quantum code we're doing, right? Well, as maybe you got from the example of Floquet code, there isn't one quantum code. If at any time you stop the protocol and you just say, okay, let me just say what the code is right now, there's going to be an answer. It will be a quantum error correcting code. Because if it wasn't, then any errors that occurred at that time would not be correctable. But the code is constantly changing in time. Right? You're doing some gates, and that changes the code. It causes the code to evolve into a different error-correcting code, which should have similar error-correcting properties, but not identical in other respects. Okay? And it could be that it's going in a cycle, like a Floquet code, or it could be that it's constantly changing and it never repeats. Certainly the most general protocol, there's no strong reason that it needs to repeat. There might be practical reasons why that's useful, though. Okay, so another question that's a little harder is, I said, well, the code could constantly change and might not repeat. So if that's the case, how do we do logical gates on these things? In fact, what does it even mean to do a logical gate? Right? If you do code deformation and end up back in the same code that you started, you can say, oh, well, let me look at the, theoretically speaking, let me look at the logical state before the deformation and the logical state after the deformation, and oh, there's been some change, I know that's a logical gate. But if the code never repeats, how do you compare the logical state at time 0 with the logical state at time 10? Right? How do you know if there's been a gate or not? And the answer is kind of subtle, and I have to say I don't fully understand this yet. But the basic idea is you have to keep track of how your logical states are encoded. Right? So you say this at time 0, this is the logical 0, and this is the logical 1. And well, now I'm in a different code over here, and so this is the logical 0, and this is the logical 1. And then maybe I'm over here, and this is the logical 0, and this is the logical 1. And what I look at then is how the actual state of the system compares with the logical basis states that I'm keeping track of. And there's some limits on what you can do here. I mean, you could imagine just saying, well, you know, forget about changing the code. I want to do logical gates. Let me just change the logical 0 and logical 1. And then the encoded state has changed relative to the thing, so that's a logical gate. And there's limits, you can do that, but there's limits to it because you have to be consistent with later things that you do, which might depend. You might not give you full freedom to pick the logical 0 and the logical 1 however you want. Okay, but like I said, I don't completely understand what the constraints are here. Okay, and then the last question is, okay, so we have this idea of how to design new fault-tolerant protocols, so how do you actually do that? Tell me how to make a new fault-tolerant protocol that follows these principles. And that I do not know how to do. That's a topic of research that I'm very interested in. Okay, so what I do want to tell you, though, is some of the results we figured out about these kind of properties of these codes, and these things, I think, can help us towards this goal of being able to design new fault-tolerant protocols that fit this picture. So to set some terminology, so a dynamical code, we go through a sequence of codes. I'm going to stick to stabilizer codes. So we can imagine that really we're just doing a sequence of measurements. And every time we do a set of measurements, that has the potential to change what the code is that we're using. And so we go through a sequence of instantaneous stabilizer groups. They're all stabilizer codes. So the stabilizer of the code at time I is going to be C sub I. Okay? And then we go to time I plus 1, and it's code Ci plus 1 through the next sequence of measurements. And I'll call this a Floquet code if it goes in a cycle, but the same formalism applies if it doesn't go in a cycle, if it doesn't repeat. Okay, so one thing that you have to be careful of here is that because we're making all these different measurements at different times, how do we ever get synchrome information, right? I mean, the normal way you learn what the errors are is you have your error correcting code. It has some particular constraints that it's supposed to satisfy, the stabilizer, right? And then you measure the stabilizer elements at a later time, and you see have they changed or not. That's your error synchrome, and it tells you what the error is. But if the code is constantly changing, you're always behind, right? You know what they were supposed to be at previous times. You don't know how they've changed necessarily. And so the thing is that what you could do is you could design the sequence of measurements so that you do eventually measure some of the stabilizers of the original. You know, if you want to find out what the syndrome was from time C1, you could eventually measure many or even all of the generators of C1. Except you might not measure them directly. You might make other sorts of measurements that when put together will tell you that measurement. And you'll see an example in a little bit. And so the question that arises is how you learn this information. And one thing about this that turns out to be important is that you don't learn them right away. Okay? You learn them over time. And that's actually helpful for fault tolerance because it allows you to kind of integrate errors that occurred over a bunch of times and collect that information to process and determine when the errors occurred as well as where. And so the concept that's needed to understand this is the idea of masking stabilizer generators. So So masking means that we have some bits of the error syndrome, some pieces of information about the error that we don't know right now, and we have not measured. And so there's kind of three ways this can be relevant. So you can have some stabilizer generators that are unmasked, where we know we've made appropriate measurement, we figured out what the error syndrome is, the bit of the error syndrome, and then therefore we know how it's changed from what it was originally. Then there's some that are temporarily masked, that we haven't measured yet, but that we will measure in the future. Okay? But there can also be bits of the error syndrome that are permanently masked, that we're never going to measure. And in fact, it may not be possible anymore to measure those because of some subsequent measurement we've made that erased those values. And so the thing is that when you have a stabilizer with masked generators, then you don't have as much error correction capability as you started with, as the code ideally has, right? Because you have less information about what the error is. And so you can think about there's the distance of the code, which kind of encapsulates the ability of the code to correct errors when you have all the syndrome information. And the unmasked distance will be less than that. That's your ability to correct errors with only the information from the unmasked generators. And so the thing is that figuring out which generators are temporarily masked, which ones are unmasked, and which ones are permanently masked, that can be kind of subtle. And it's not really obvious looking at one of these dynamical code protocols what is going on there. And so let me show you an example of how it can be subtle. And this will also show you how you can kind of extract information over time from multiple measurements. So these two examples are going to start the same way. We're going to have a stabilizer that has two generators. One of them is XXX, which could have a value +1 or -1, eigenvalue +1 or -1. And one of them is ZZI. Okay? And we'd like to measure the eigenvalue of XXX. But we're not going to do that. Instead, we're going to measure other things. So first we measure just X on the first qubit. Okay, and we measure X on the first qubit. Well, that's going to give us a random value because it anti-commutes with ZZI. So it kicks ZZI out of the stabilizer. That's no longer a constraint on the code. And instead we have -1 to the b XII because we got the value b. Okay, and so then in the first example, after that we measure Z on the first qubit. Well, we measured X on the first qubit, so measuring Z on the first qubit, that's certainly going to be random again. And moreover, Z on the first qubit is incompatible with this state being an eigenstate of XXX, because Z and XXX anti-commute. So XXX gets kicked out of the stabilizer, but XII also gets kicked out of the stabilizer. However, the product of them, which is -1 to the a plus b IXX, that still commutes with ZII, so it's still in the stabilizer. And we already learned B, we learned C, and so now if we measure IXX, we can put that eigenvalue together with this, the eigenvalue B that we've already learned. So we learn A plus B by measuring IXX. We learned B earlier on, and so we can put those together and figure out A. Okay, so the stabilizer XXX from the original instantaneous stabilizer group has become unmasked. So that's great. So now we know what that is, and we can use that for error correction. So let's compare to the second example. So in the second example, well, we start the same way. We start with the same XXX and ZZI stabilizer. We measure XII, but instead of measuring Z on the first qubit, we measure Z on the second qubit. Doesn't seem like a big difference. But now, the thing is that IZI, it commutes with XII. So X on the first qubit, that's still in the stabilizer. But XXX still does not commute with IZI, so it gets kicked out. And now the stabilizer -1 to the C IZI and -1 to the X XII, -1 to the B XII has no information about A left. Right? So no measurement we make at this point is going to tell us what A is. We've erased that information. And so in this example, XXX is permanently masked. So we made this one small change, measuring Z on the second qubit instead of the first qubit, and it gives us a totally different result. Okay? And so that's why this is subtle, and it requires some work to figure out what's going on. Anyway, so I have limited time, so I'm not going to explain how we actually do figure this out, but the paper by Xiaozhen and I explains an algorithm that will determine, given a sequence of measurements like this, which generators from the original, the stabilizer at time 0 are unmasked at any given time when they're unmasked, and which ones are permanently masked, which ones are temporarily masked. And so the other thing about having an algorithm like this is it helps you analyze and understand other possible behaviors you can get from these dynamical codes and from flow K codes. So again, a flow K code is one where you go in a sequence, where you measure the same measurements over and over again in the same sequence, okay? And so let's assume that the number of rounds of measurements you make, a round has some number of commuting measurements, is a constant, even for a very large system. So my expectation, for instance, was that, okay, if you do that, then anything that becomes unmasked should become unmasked after one cycle or so. Because then you're just repeating the same measurements over again, right? It should be the same. But actually that turns out not to be correct. Not only is it not correct, it's not even close to correct, because actually if there's n qubits in the system, it can take order n rounds, order n full cycles, before everything is unmasked. And similarly, if you start with some unencoded state, and you do this sequence of measurements repeatedly, in order to initialize the flow K code, it can take order n cycles in order to finish that initialization before the code stops changing. So that, like I said, that to me was surprising, but it comes out of understanding this process of masking and unmasking. So, okay, so then let me summarize. So I think this approach of dynamical codes is a possible way to improve our existing protocols, potentially by a lot. Maybe it won't help, but I don't see any reason why it wouldn't. It opens up a wide variety of new protocols. And it gives us a new insight to how fault-tolerant protocols can work. So the thing is that a lot of the behaviors dynamical codes can be different from regular static quantum error-correcting codes. So for instance, another open question is, we have a lot of existing constraints on error-correcting codes and how they can behave. Do those constraints still apply to dynamical codes? Probably some of them do and some of them don't. And so again, the picture that I want to develop is one where we have a space-time view of everything. We look at the whole circuit together, put space and time on an equal basis. And instead of trying to limit error propagation, we try to identify the space-time location where the faults occurred and track the propagation from there. I don't really know how to design protocols in this. Like I said, that's a great open problem, but probably a big undertaking. But for me, this is an exciting way forward that can potentially give us new fault-tolerant protocols that look like nothing we have right now. So thank you, and congratulations again.
Questions, please? Yeah. I can wait to you.
There's a microphone here.
So my question is, so like this is all very elegant theory, right?
Yeah.
It talks about things like truth, information, and color talking. But like, how do you test these assumptions? How do some of these others that it accurately follow what is actually going on?
Right. So I mean, so the thing about the field of quantum information is that we're assuming that quantum mechanics is correct, right? I mean, we're not blindly assuming that, but we do experiments, we try to build quantum computers, and they seem to agree with the laws of quantum mechanics. And so we can mathematically prove within the structures of quantum mechanics that quantum error-correcting codes will behave this way, given some set of assumptions about, say, what the errors are. Now, it could be those assumptions about the errors are wrong, and those are things that get tested by experimenters. But so far, it seems to hold up. Quantum error-correcting codes do seem to work in the experiments that people have done. Maybe not as well as we would like, but that's because the errors are bigger than we would like. Now, what I've been talking about today of these dynamical codes, it's more of an idea for direction than a concrete thing. It may be that they won't pan out, they won't help, or it will be too hard to design stuff like that. And so, yes, the onus is on me and people I can convince that this is a good idea to come up with concrete examples that could be implemented in real systems. And you can see that they work then.
Hi, Daniel, very nice talk. I'm trying to understand your concept of time here. Is it a universal time? Is it uniquely defined, or are you thinking of the time as a general relativity? It's up to the observer to define what he means by time in your setup?
No, nothing so subtle as that. So I'm just thinking of time in a regular circuit model, time where you have some clock. Okay, let's take the idea of a quantum computer that's controlled by a classical computer that says, okay, do this gate now, which is frequently the case. Then at time 0 it says do this set of gates now. At time 1 it says do this set of gates now. Time 2 it says do this set of gates now. And so that's the only time I'm worrying about here. You can assume it's discrete. That's not really important for this bigger picture, but it's obviously a helpful simplification in order to, this is hard enough as is. If we try to do, continuous time or, different time reference frames, even special relativity, let alone general relativity, it's going to be much, much harder. Let's start with the simplest case first.
More questions?
Thank you for the great talk. So my question is, these are dynamical codes in the sense that they change between time slices.
Yeah.
Are they predetermined or are they adaptive? Can we get to change something in the middle?
That's a great question. So there's absolutely no reason that they have to be predetermined except practicality. From everything I presented, absolutely, you should, ideally, you should be collecting information about the errors and, so let's assume that you know ahead of time the logical circuit you want to do. So you can plan based on that. But the information that you get about errors is something that you don't know ahead of time. And so, in principle, yes, you should collect that information. It's only going to be partial information, but that can maybe steer you to doing one code or another. The other thing that can happen is you're doing gates. Sometimes you make some measurement and you don't control what the outcome is. And it may be for one outcome you want to go in one direction, and for the other outcome you go in a totally different direction. So that's definitely a possibility. Now, it may turn out to be impractical in real time while your quantum computer is running to make those decisions and to keep track of what's going on and to come up with the appropriate decoding algorithms. There's a lot of extra computational overhead that goes along with adaptive coding like that. But maybe it's possible, and maybe it sees improvements. But that's something that we just don't know yet.
Thank you. Just a quick follow-up question. So in terms of if you decide to make it adaptive, then do you think it's possible to make it passive adaptive so that it automatically, you design it in a way that it automatically changes the tomography of the code?
What you mean by passive adaptive, or just in general passive things, is not in some sense really passive. What it means is that there's some natural dynamics of the system that are changing things in a particular way, and you don't have to do anything. That you're fine with that those dynamics are helping you, and maybe that's possible. Obviously, if you can do that, that's very attractive. Again, I want to start with the simplest case where we get to pick everything and try to work from there.
Thank you so much.